Okay, so we're going to go on to building your code. And the first slide is a discussion of SoftIns. SoftIns is a tool for managing your environment. Think of it as being akin to .kit on the TriLab systems or environment modules on a Cray or an NSF system. It sets your paths and LD library paths and other environment variables to where they should be to use a given piece of software. The settings are maintained in the root level of your home directory, so tilde.soft on Mira, Cetus, or Vesta, or tilde.soft.cooly for changing SoftIns symbols on cooly. By adding and removing keywords from the .soft or .soft.cooly, you can change your environment. The only thing to watch out for is to make sure the @default is at the very end. @default provides things along the lines of bin and user bin and base system libraries that you need for important things like your shell to actually work and function. Commands that are important to the functionality of SoftIns or SoftIns, which lists all keyword defined on the system. Resoft, which will reload your .soft or .soft.cooly file, depending on the system that you're logged into. And then on the command line, you can use soft add or remove followed by a keyword to temporarily modify your environment. It's important to remember that when you use soft add or remove, that you are only temporarily modifying the environment and that a resoft will immediately restore you back to whatever was in your .soft. So we provide and support 3 sets of compiler wrappers. And the compiler wrappers are similar to the MPICC or MPICXX that you would find on any system with MPI. The first set of compiler wrappers is for the IBM XL compilers. These are vectorizing compilers from IBM. Their last update was October 2017. When you add plus MPI wrapper -XL, you'll find it in your environment in MPICC, MPI XLC, MPI XLCXX, MPI XLF77, MPI XLF, and MPI XLF95, and then MPI XLF 2003. One thing to watch out for is if you're working with threads or codes that are sensitive to OpenMP or pthread parallelism, you will want to add an _R to the name of the wrapper that you're using to make sure things are thread safe. I generally just add the _R and use and do everything thread safe by default. One important option or useful option is if you would like to see exactly what the wrappers are doing, you can always add a -show following the wrapper name and just run that on the command line, and it'll show you exactly what the wrappers are going to do. Similarly, there's a wrapper for the GNU cross compilers, which is plus MPI wrapper -GCC. Again, the names are relatively predictable: MPICC, MPICXX, MPI-F77, and MPI-F90. And then there's another set for Clang. Clang is actually, if you are a C++11 or later user, it's basically your best and only hope for support. And those wrappers wind up being named MPI Clang, MPI Clang++, or MPI Clang++ 11. There's a little more discussion within our web pages for software and libraries. One important thing to think about is MPICC it actually exists for all sets of wrappers. And so if you're not sure, it's always worthwhile to just do a quick show and see exactly which compiler and which version of the compiler is being invoked along with which libraries. To kind of continue the discussion of the IBM XL compilers, optimization flags kind of behave the way that you would expect with -O0 through -O5 with the only mission being O1. Most users tend to find the best performance with either O2 or O3. O4 and O5 supposedly add IPA interprocedural analysis. However, in practice, most users find that it tends to lead to a very fragile binary and just add the compiler time and binary size without a lot of return on the investment. If you're debugging, your best option as always is O0. For most day-to-day work, correctness checking, baseline performance, O2. And then if you're relatively sure of how things are, O3. So when you're using the IBM XL compiler, there's certain optimization tips. You can add in a -q list opt to show all the flags that were used in compilation of a given unit. Q report to give you a report on what the optimizer did. As previously mentioned, as you go up from O2 and O3 to O4 and O5, performance can actually decrease. It may be worth investing some time to see if what exactly takes place as you raise optimization levels. And it may also be worthwhile invoking different flags to see exactly what may have slowed things down going in up to 04 or 05. One other important flag is -G, which tells the compiler to include debugging information and resolve code line numbers. For the most part, we recommend not turning debugging off and instead just by default compiling with -G. For the most part, it seems to make life easier for both you and for the ALCF staff while debugging. In terms of threading support with the XL compilers, the base flag is QSMP equal OMP : no auto. So that basically says just turn on OpenMP support and don't attempt to automatically provide any sort of threading. For the GNU compilers and the Clang compilers, the flag is -F OpenMP. pthreads is supported. It's the nptl pthreads implementation in glibc. You shouldn't require any sort of modification. There's no special sauce for working on the blue chain with pthreads. There is auto thread parallelization available with the XL compilers by adding -QSMP equal auto. My personal experience is not only is it effective, it's often a little bit slower to make some interesting life decisions. But if your threads don't contain any sort of external dependencies and your functions are relatively short and relatively clean, it's usually a safe option to throw in just to see what will happen. One important thing to think about is the run job mode will determine the total number of threads, including the master thread available. There is, for run job, you want to put specifying -- ranks per node, or if you're using non-script jobs, q sub -- mode, and we'll come back to that in a minute. There's a maximum of 4 threads per core. That means that there's a possibility of up to 64 threads per node. And to obtain peak efficiency, when using, you will need at least 2 threads per core. And that's basically to make sure that the QPX units and all the communications units stay saturated. Speaking on OpenMP, again, shared memory parallelism, more threading is supported within a single node. Most of our users have some form of hybrid programming model with OpenMP at the outer layer across the compute node, OpenMP at the inner level within the compute node. Again, for the XL compilers, you should be using the thread-safe compiler version. That is to say, again, the _R. And that's true whether you're using OpenMP or pthreads or threading building blocks or anything else. OpenMP directives as of version 3.1 and earlier supported, so that's parallel 4 sections, critical single. Those directives are all supported. Newer features from OpenMP 4 and later are not supported, and the pragmas are exactly what you're expecting as they would be on any other platform. So in C or C++, hashtag pragma OMP, then the rest of pragma, or bang $ OMP, followed by the OpenMP directives within Fortran. There are compiler functions that can also be used, though most folks use the pragmas. And then to control the number of OpenMP threads, it's just like any other Linux system where you set the environment variable for run job or within your queue sub for OMP num threads. So moving forward, if there aren't any questions, we'll move forward to software and libraries on the Bluechain queue systems. So we support two sets of libraries, the first of which is the IBM system and included Bluechain drivers libraries, and those are located within BGSys drivers PowerPC floor. For the most part, the compiler wrappers take care of all of that for you. But what's within there is glibc, so basically libc, impitch, which is our MPI, and PAMI, which is what the Bluechain version of impitch is built on top of. Separately, there's the libraries that ALCF supports, which are located in /soft/libraries. And these are things like ESL, PETC, HDF5, NetCDF, PNetCDF, Boost, BLOS, LAPACK, various FFTs, certain search libraries, interpolation libraries, quadrature, random number generators, and blocks. And there's some additional tune libraries which we support within soft libraries ALCF, which again are things like BLOS, CBLOS, FFTW2 and 3, LAPACK, Metis, Parametis, PARPAC, ScalaPack, Silo, SZIP, and zlib. And again, their online documentation goes into a lot more detail. For the most part, we try to keep the number of things that we provide direct support for relatively small, but we try to make sure that what's provided is very well supported and very well documented. Likewise, there's a number of library directories under /soft, which contain tools for performance profiling and debugging. Within /applications, there's builds for things like LAMP, SNAMD, QMCPack, and their level of support varies depending on your catalyst and your project. /soft build tools, which contains relatively up-to-date builds for AutoTools, CMake, and Doxygen. /soft compilers, which contains the IBM compilers, as well as builds of Clang. /soft debuggers, which contains the DDT debugger, and there may be an install of TotalView, but I do not believe the license is current. /soft libraries, which, as I previously mentioned, are where you would find the math libraries and parallel IO libraries. And then /soft perf tools with performance tools like Tau, HPC Toolkit, PAPI, OpenSpeedShop, Scholastica, and the like.